All right, welcome to The Explainer. Today, we're diving into something truly fascinating, the world of organic chemistry. It's a world that seems incredibly complex, but it's all built on a kind of hidden language. And that's a really good question, right? I mean, think about it. There are literally millions of different organic molecules out there. They're in the food we eat, the clothes we wear, the medicines that keep us healthy. So, how on earth do chemists keep them all straight?
Well, here's the secret, the big idea for today. They learn the language of molecules. You see, organic chemistry isn't just about memorizing a bunch of random facts. No, it's a full-fledged language. It's got its own vocabulary, its own grammar, and once you get the hang of the rules, you can start to understand and even speak it.
So, if we're going to learn this language, where do we start? Well, every language has its descriptive words, right? Its adjectives. In chemistry, these are the parts of a molecule that give it its character, its unique personality. And we call this a functional group. You can think of it as the action hero of the molecule. Seriously, it doesn't matter how huge the rest of the molecule is, the functional group is where all the interesting stuff happens. It's the part that actually reacts with other things. It's what gives a molecule its specific properties. Its function. So let's look at a few. You can really think of these as the verbs or adjectives of the molecular world. An alkene, for instance, with that carbon-carbon double bond, it behaves in a completely different way than, say, an alcohol with its little OH group. These tiny clusters of atoms literally define what the molecule does. Okay, so if functional groups are the adjectives, what about the nouns? The basic building blocks of our sentences. Well, that would be the carbon chains. Say hello to the alkane. This is really the simplest family in all of organic chemistry. It's just carbon and hydrogen atoms, all connected by simple, single bonds. They're the basic framework, the skeleton, that all those other interesting functional groups get attached to. Now, you can imagine that drawing out every single one of those carbon and hydrogen atoms, well, it would take forever. It's just not practical. So chemists came up with a really clever and honestly kind of elegant shorthand to draw them. And the rules for reading these skeletal structures are so simple. Every corner you see, or every endpoint of a line, that's a carbon atom. The lines themselves are the bonds. And the hydrogens? We don't even draw them. We just assume each carbon has enough hydrogens attached to make a total of 4 bonds. It's simple, it's clean, and it's way faster. All right, so let's recap. We've got our nouns, the alkanes, and our adjectives, the functional groups. Now, we need some grammar. We need a set of rules to put it all together so we can give these molecules names that everyone, everywhere can understand. And this is where a group called the UPAC comes in. That's the International Union of Pure and Applied Chemistry. They created a universal naming system. And this is a huge deal because it means a chemist in Tokyo can read the name of a molecule and draw the exact same structure as a chemist in Rio de Janeiro. It's a truly global language for science. And what's cool is that it's not really about memorizing things. It's more like solving a puzzle. There are just 3 basic steps. First, you find the longest continuous chain of carbons. That's your parent chain. Second, you number that chain, starting from the end that's closest to any branches. And finally, you just name those branches and say which number carbon they're on. That's it. Every molecule gets its own unique, logical name. Okay, so we've got the vocabulary, we've got the grammar. We can draw molecules on a flat piece of paper and we can name them. But everything we've talked about so far is missing a huge piece of the puzzle. This is where things get really interesting. Think about it. Are molecules really just flat, static lines on a page? Is that the whole story? No, not even close. In reality, those single bonds we've been drawing aren't like rigid sticks. They can actually rotate. This means molecules are constantly twisting, turning, and folding into all sorts of different 3D shapes. We call these shapes conformations. And this idea, well, it changes absolutely everything. But here's the thing, that rotation isn't always comfortable for the molecule. As those bonds spin around, the electrons in them can get a little too close for comfort, and they start to repel each other. It's like they're invading each other's personal space. This creates a kind of stress and energy cost that we call torsional strain. And just like us, molecules will do just about anything to avoid stress.
Let's just look at a super simple molecule, ethane, to see this in action. When its hydrogen atoms are spread out as far as possible, we call that the staggered shape, there's basically no strain. It's relaxed and stable. But if it twists so the hydrogens are lined up right behind each other, that's called eclipsed, the strain goes way up. So what happens? The molecule overwhelmingly prefers to be relaxed. In fact, at any given moment, something like 99% of all ethane molecules are chilling out in that stable, staggered shape.
Okay, so now let's take this whole 3D idea and apply it to something even cooler, molecular rings. This is where we really see molecules performing some incredible gymnastics to find the most stable, comfortable shape possible. See, for a molecule to be truly stable and happy, it has to avoid 3 different kinds of strain. First, angle strain. That's when its bond angles are forced to be something other than their ideal shape. Second, the torsional strain we just talked about from eclipsed bonds. And third, something called steric strain, which is basically just atoms physically bumping into each other. They're too crowded. So let's put a number on this. There's a really common ring molecule called cyclohexane. It can twist itself into a shape that, well, kind of looks like a boat. The problem is, this boat shape is super unstable. It's full of strain, about 29 kilojoules per mole's worth. And trust me, in the molecular world, that is a lot of stress. But cyclohexane has a trick up its sleeve. It can twist and fold into a different shape, a much, much better one. It's called the chair conformation. And this shape, it's incredible. Compared to the boat, the chair has pretty much 0 torsional strain and 0 steric strain. All the atoms have their space, the bond angles are almost perfect. It is by far the most stable shape it can possibly be in. Really, this chair conformation is a masterpiece. It's the perfect example of everything we've talked about. We went from thinking about flat lines on a page to understanding that these are dynamic 3D objects, and the chair shape is the ultimate proof. It's a molecule that has twisted itself into the most perfect, stress-free, low-energy state you can imagine. And that really brings us to the big takeaway. In chemistry, and you could argue in life, structure determines everything. The way something is put together, its fundamental shape, defines what it is and what it can do. Thanks for joining me on The Explainer.